nanostructured materials or preparation of nanostructured materials. You can also have another terminology, fabrication of nanostructures. Last class we have seen what are the two prominent methods one can synthesize nanostructured materials. What are the different methods under which we can create nanostructures? What are their advantages, disadvantages? What are the merits, demerits associated with those two prominent methods we have seen? We have also seen what are the great challenges associated with the generation of nanostructured materials. It's not as simple as what we think. There are great challenges one has to face, want to synthesize nanostructured materials. What else we have seen? Those who attended a previous class on this unit, they can respond. Even others also, if they can.
New nanoparticles.
One by one. Yeah, please. What are the two prominent methods one can create nanostructures?
Physical and chemical methods. Sir.
Physical and chemical method. Physical method is also known as
Top-down method.
Top-down method. Chemical method is also known as bottom-up approach. You build the nanostructures from a bulk material by subdividing into nano. No reaction is involved, but lot of wastage is involved, is associated with. Ball milling, sputtering, laser ablation, physical vapor deposition are some of the examples. You can also build the nanostructures from molecular or ionic precursors by conducting some chemical reactions. Definite involvement of some chemical reactions in chemical method. That's why the name chemical approach or chemical method. Since the nanostructures are built from the ionic or molecular precursors, which are lesser in grain size compared to the nanoparticles, so they are also, this method is also known as bottom-up approach. This is a schematic view of both the approaches. From bulk material, you get nanostructure. From ionic and molecular precursors, you get nanostructures. In both cases, you are going to get nanograins, nanomaterials. Correct? You believe it or not, this cartoon or image is taken from my PhD thesis. 20 years before I created this. So what else we have seen? Anybody else would like to respond? Am I audible?
Yes, sir.
Yes, sir.
Screen is visible?
Yes, sir.
I hope it is recording. Do you see recording symbol?
Yes, sir.
Yesterday I had recorded,
Yes, sir,
but
it is
there was
recording.
no display. Only my portrait was there. I don't know what was the problem. I hope it's not same here today. Hope it records the screen also. Yeah, say anybody else would like to add anything else we have seen that we have seen in the last class? Four important parameter are
Yes, sir. We also
we
seen
have
about
seen challenges associated with the generation of nanostructures. What are those four challenges? Anyone remember?
supersaturation, nucleation, crowd. Yes, sir.
That is process of
Supersaturation,
precipitation.
nucleation, crowd.
This
Either
is
different size, sir.
no. I am talking about this. Fundamental issues to get identical size of all particles or to get the mono-sized particle or uniform size particle is very important. And it is a great challenge. Simply, it is not possible to get unless you make some effort in the synthetic process. What are mono-sized, uniform-sized particles? Like this. I am repeating a little bit so that the newcomers also will understand. To get such morphology or to get such canopy or grain sizes is great challenge. It may be gold, silver, platinum, titanium oxide, silicon oxide, nickel oxide, anything. You see that each particle or each grain is similar, highly spherical, same size. But here, spherical, but different sizes. Properties of this material will be different. Properties of these grains will be different. Getting identical size or mono size is very important and it is a challenge. Identical shape also very important. Identical size, identical shape. What is identical shape? You see here, all particles are nearly cubical. All particles are nearly cubical. But you look at here varying shape. Identical shape or same size, same shape. But here varying shape, different shapes. You see cubical, hexagonal, okay, sometimes nearly spherical, elongated spherical, or some heart shape and no shape, different all sort of size shapes we have. Again, properties of this will be different, properties of this will be different. Then when you are making the composites, alloys or composites, what are alloy? What are alloys? What are alloys? Excuse me. What are alloys?
So the combination of two metals which is inseparable.
Yeah, combination of two metals, if you make it an homogeneous solution, solid solution, it's an alloy. What is a composite? Any two entities mixed with some ratio need not be metals. They are composites. Titanium oxide carbon mixture is a composite, whereas bronze is an alloy. Copper zinc alloy, nichrome, you would have heard about it, nickel chromium alloy. Gold silver 50-50 composition is an alloy. So if you are making some composition, that composition should be identical throughout the matrix or throughout the particles and should have the same crystal structures, same crystal structure. Then fourth challenge is to get agglomerated particles. To get the agglomerated particles. What are agglomerated particles? I hope this slide will give you better information. You see here, some particles, maybe gold particle or silver, titanium oxide, silicon oxide, anything. Highly dispersed. What I mean by highly dispersed? Each entity, each grain is separate. They are not touching each other. They are not touching each other. Looks like they are maintaining, all of them are maintaining social distance. But whereas here, looks like this is pre-Corona, Corona or Corona. Everybody held together. Here also held together. This state of grain is known as highly dispersed. This state of grains are known as agglomerated, aggregated. Aggregate, right? We have seen previously in the first unit aggregates. Single particle is a particle. You bring several particles together, you get an aggregate, agglomeration, leading to aggregates. And this is dispersed. You believe it or not, properties of this will be different, properties of this will be different, even though it may be a same material, even though it may be made up of same gold or silver, platinum, or anything for that matter. I think this is what we have stopped in the last class. I have repeated a little bit so that it will be beneficial to the newcomers. Okay, so I think this has become problem. One by one, people are coming. I have to go back. Several times I have to go back. It is disturbing. Please, all of you join on time. Otherwise, don't join. So it is disturbing. Okay, so this is what we have stopped in the last class. There are 4 fundamental challenges in synthesis of nanostructured materials. They are to get identical size, identical shape, identical composition, and highly dispersed particles. Of course, as others have told, so there are in the case of chemical methods, these 3 fundamental phenomena are taking place. There should be a supersaturation. Once the supersaturation takes place, you will have a generation of nucleation. Once the several nuclei are formed and they can undergo growth, leading to precipitations. These are the fundamentals that we have seen in the last class. When you bring 2 solutions together, definitely there will be some chemical reaction. The least would be at least a precipitating reaction. I told you an example. Take tap water containing chloride and add a silver nitrate solution. A silver chloride will be precipitated. Is a typical example for precipitating agent. You are asked to test this experiment during 11th standard. Maybe in some campuses, maybe earlier to 11th standard. If not in 11th standard, at least 12th standard, you would have tested this. Precipitation. Or you can add some reducing agent that need not be in the liquid state, can be any state. Then something will be reduced. Metal ion will be reduced to deposit or precipitate as metals. This is the basis of chemical approach. This is the basis of chemical approach. A simple example would be to get gold nanoparticle. These dark grays are gold particles. Okay, so you take auric chloride as a precursor molecule, HAuCl4, then add sodium borohydride as a precipitating agent or reducing agent. Then conduct the reaction 10-15 minutes. If the campus is open, we will have this experiment. It's part of the practical. So both green synthesis and chemical synthesis. And you are done and you will get very high magenta color or red color gold solutions, colloids. So we will also have, in addition to these 2 precursors, we will also have thiols. Please wait for 1 or 2 classes more. What is the role of these thiols? I will be able to explain. So to inform you, it will protect the particles, gold particles. It can provide like an army so that nobody can touch this gold particle. Why it has to be protected, how it has to be protected, what are the methods of protection, maybe as we go along, we will learn. Okay. So there are 4 great challenges associated with the synthesis of nanostructured materials. Irrespective of the methods that are used for synthesis of nanostructured materials, they can be grouped under these 2 categories: thermodynamic approach and kinetic approach. Thermodynamic approach and kinetic approach. So what the name thermodynamic approach mean? When we say thermodynamics, what it talks about? Can anyone respond? Generally, when I say thermodynamic, what do I mean? or what we can connect generally.
Equilibrium.
Yeah, so thermodynamic talks about spontaneity of the reaction, whether the precipitation process will occur or not, whether the deposition process will occur or not, whether any nanostructure can be synthesized or not spontaneously. Methods linked with the thermodynamic approach deals with the spontaneity. And it involves, generally we have seen that creation of supersaturation, nucleation, and growth. Whether gold can be synthesized or not, thermodynamics can predict. Whereas generally kinetic approach will talk about how quick or how slow you can get the gold precipitate using any method. So the take home point today is this from this slide is thermodynamics talks about the spontaneity, whether the process will take place or not. Kinetics talks about rate of the reaction, speed of the synthetic process, or velocity of the synthetic process. How quick or how slow you can get some nanostructures for that matter. When we say thermodynamics, definitely we have to link thermodynamic quantity. When we say thermodynamics, we have to link with the thermodynamic quantities. Can you name one or two thermodynamic quantities? It may be too simple, I'm sure. So I am taking you to 11th standard, 12th standard, or your first year engineering chemistry, something like that. What are the thermodynamic quantities?
Sir, velocity, force,
Entropy, etc.
acceleration.
Yes, please. So the first and foremost thermodynamic quantity is a free energy change. You would have heard about free energy change, or the other name for free energy change is Gibbs energy or Gibbs free energy, and it is symbolized in delta G. For any process, if delta G is negative, it is thermodynamically possible, spontaneous. Any process, whether you conduct in the lab, elsewhere, or any natural process, or there is a saying, all the natural events are thermodynamically spontaneous process. All the natural processes are thermodynamically spontaneous process. For example, water can drain from the uphill to down without any effort. It's a thermodynamic process, thermodynamically spontaneous, and it is irreversible process for that matter. Whereas to take water from ground to the uphill, you have to spend energy. You have to spend the energy. It flows from high temperature to low temperature automatically without doing any effort. It's a thermodynamically spontaneous process and it is irreversible. If you have to reverse it, you will have to make an effort. You will have to spend energy. When we have a concentration gradient, the system tries to attain the equilibrium by becoming dilution from high concentration to low concentrations automatically. Whereas kinetic approach talks about how quick or how slow a process can take place. Thermodynamics says that diamond can form, but we know from the kinetic approach that it takes decades of or millions of years to get the diamond. Very slow. And as you see, the rate or the velocity or the speed of any process is limited to the availability of the precursor molecules in the reaction vessel. If in the reaction vessel, if there are no precursor or if there are no starting materials, we cannot expect any growth of the particles. So highly limited. The reaction rate is highly limited. Okay. So let's see. Let's go further. Are you with me? Shall we go ahead? Anything difficult? Is it easy to follow? Shall we go ahead? Yes, right? Am I audible? Yes. Okay. So we have seen that there should be a supersaturation creation. Yes, please.
Sir, will you provide us these slides?
Yes, definitely.
Okay.
Video also will be provided.
Okay, sir.
But I advise during the classes, you can note down some points because everything may not be there in the slide.
Yes, sir. I am writing some points.
Yeah, if possible, you can write down, all of
Yes.
you.
Yes, sir.
So when you bring two solutions together, there should be a creation of supersaturation. That will lead to the creation of nuclei. When I say nucleation, so if the nucleation is created from the same phases, maybe from two solutions, or maybe from two solid surfaces, or maybe from two gas phases, two different material, but they are in the same phase. Here is one liquid, another is another liquid. Both are liquids, but different starting materials, precursors. And when you bring them together, they can undergo supersaturation and create nuclei. Since the nucleation is created from the same phases, we call this nucleation as a homogeneous nucleation. Whereas, if the nucleation is created from two different phases, for example, one material is in the solid, another material you are adding either liquid or you are passing some gaseous molecules. Then the reaction is taking place. How? There should be a creation of nuclei. Creation of a nuclei from two different phases is known as heterogeneous nucleation. It's as simple. It's simple. So as we go along, I will distinguish these homogeneous nucleation and heterogeneous nucleation in a different way later. Please wait for that. So this is from the starting point, the phases of the starting materials. Two types of nucleation we can have: homogeneous nucleation and heterogeneous nucleations. But definitely we need to have a nucleation. Then only growth can take place. Once the growth takes place, so we can have a precipitation. You can precipitate maybe gold, silver, cadmium sulfide, titanium oxide, or anything. So at least one nucleation should take place. So to start with, let us consider homogeneous nucleation. When this homogeneous nucleation will take place? When we have two identical phases. For simplicity, we will consider two solutions. Tap water containing sodium chloride or sodium chloride. Another solution containing silver nitrate, or a solution containing auric chloride, HAuCl4, which can be a precursor for getting gold nanomaterials, nanocolloids. Then another solution containing sodium borohydrate. This sodium borohydrate, as I told a few minutes before, it can act as a reducing agent as well as precipitating agent. When I say reducing agent, something is reduced. What we can expect in this case? Go Am I visible now? My screen is visible. Voice is audible?
Yes, sir.
Okay, okay.
Yes, sir.
Yeah, we will encounter like this sometimes or many times. We'll have to cope up. Yeah. So homogeneous solution means homogeneous nucleation means nucleation from the same phases. For simplicity, we will consider nucleation from the two solutions. Solution is nothing but a solid dissolved in a solvent. Sodium chloride dissolved in water is an example for a solution. Auric chloride dissolved in water is a solution. Sodium borohydride dissolved in water is a solution. Now you bring this auric chloride solution and the sodium borohydride solution together and try to mix them. What should happen? The first step is there should be a creation of supersaturation. There should be a creation of supersaturations, followed by nucleation. Then growth should take place. When the growth takes place, there will be a creation of new solid phase. There will be a creation of new solid phase. When this new solid phase can take place, when we have this condition, when the concentration of the solute is greater than that of the solubility, a precipitate or a new solid phase can form. Okay, so now I introduced one new terminology, solubility. What is solubility? Something undergoing soluble, right? That is the solubility, ability to be soluble. You take sodium chloride, go on adding in the water, it dissolves to the maximum extent, and you create a saturated sodium chloride salt. Okay, so how much you are dissolving? So there is a constant solubility. So that should be less compared to the concentration of the solid you are adding in your mixture. So if the concentration of the solute is less than solubility, it will remain in a solution. It will remain in a solution. Okay, so this is the one condition. When such a solid can form, again we have to go back to thermodynamics. Unless the thermodynamic energy is reduced, in a system or for a system, there cannot be formation of any precipitate. There cannot be formation of any precipitate. It's something like this. In a solution, which is a mixture, a solution containing solid dissolved in solvent. And the energy of this system, Gibbs energy of this system is said to be high. We know that any high energy system thermodynamically is unstable. It has to get stabilized. How? It has to lose the energy. It has to lose the energy. How it can lose the energy? Instead of being homogeneous solution, when you bring two solutions together, a precipitate is segregated. Okay, so first condition is concentration of the solute should be greater than the solubility. Then this mixture containing high energy state, which is unstable, it has to get stabilized by losing the energy. When it happens, so the energy of the system is reduced. Okay, so you have a static material and product. Energy of the product is reduced less. Then this energy of the reactant is very high. What is free energy change? Energy of the product minus energy of the reaction or reactant. Automatically, delta G will be negative. For any process, just now we have completed, if any process associated with the negative free energy change will be spontaneous. So it means when a precipitation occurs, when you bring two solutions together, automatically thermodynamics is taken care. It means the change in free energy of this system is negative. And that is the driving force for the formation of solid particles with the help of creation of nuclei and further growth. So let us quantify this. So this is volume free energy change. So we know when you bring two solutions together, there is a creation of solid particles. Assume that the particle is spherical. And when we have a spherical particle, we have a radius. When we have a radius, we can calculate what is the volume of that particles. First unit we have seen. If you know the radius, you can calculate the volume, or vice versa. This is volume free energy change is equal to minus kT by omega ln C by C0, or minus kT by omega ln 1 plus sigma, where sigma is nothing but so C minus C0 divided by C0. What is C? C is concentration at any time. C is saturation concentration. concentration. C0 is saturation concentration. C is concentration at any time. C0 is saturation concentration. So then if sigma is equal to 0 in this equation, what will happen to delta GB? If sigma is 0, what will happen to delta G? So this equation will become minus kT omega ln 1 plus 0. Sigma is 0. What will be the value of delta G? As you see, it will become minus kT ln omega minus kT by omega ln 1. Ln 1 is 0. Log 1 is 0. So then delta G will become 0. What does delta G equal to 0 mean? 0 means it is in equilibrium process. No nucleation will take place. When delta G is negative, it is spontaneous. When delta G is 0, no reaction, no nucleation, it is said to be under equilibrium. What will happen? What phenomena will take place when we have a delta G positive for any process? Very important, these three terms. Delta G negative, delta G 0, delta G positive. Very important, fundamental. When delta G is positive for any process, that reaction will not take place at all. That reaction will not take place at all. Okay. So then to get a precipitation, this C must be greater than C0. So then sigma will be non-zero. If sigma is non-zero, so this delta GB minus equal to minus kT by omega into ln 1 plus non-zero. Let's assume 1. Then it will become ln 2 minus kT by ln 2 will have some negative delta G. And we are talking about homogeneous nucleation, synthesis of nanostructures from two identical phases, liquid phases, simply. And for that system, delta G is negative. When this condition is met. When the delta G is negative, a spontaneous nucleation will take place. Spontaneous nucleation will take place. Once the nucleation takes place, let's say, so in a vessel, you have some concentration of the reactant and another reactant, you are bringing together and supersaturation created, nucleation is also created. How many? Hundreds, thousands, lakhs, 10 power 23, more than that. All those nuclei, nearby nuclei can combine together and make a solid particle growth, precipitate. Okay, a nucleation will start forming. So then a solid is forming. Assume that the solid formed is a spherical particles. When we have a solid spherical particle, and you can characterize it with either diameter or radius. So for simplicity, radius. Okay. Radius r. Then you can quantify, apart from delta G, this surface energy you can quantify, because there is a solid is formed. When a solid is available, definitely it will be associated with its surface energy. How much it is? Delta mu is equal to 4 pi r square sigma. This is sigma. This sigma is different. This is gamma. Yeah, this is gamma. From your two solution, thermodynamics favors formation of nuclei. A solid is formed at the expense of having a negative free energy change. A solid is formed will have associated surface energy, and it is nothing but delta mu is equal to 4 pi r square gamma, where r is the radius of a solid particles. Then we have two phenomena. volume energy, that is volume free energy, delta GV, and surface energy. Both should be balanced in such a way that a total free energy change is less than zero or should be negative. Then a solid will be precipitated. A solid will be precipitated. Volume free energy change you can quantify related to volume free energy change 4 by 3 pi r cube, and surface energy is 4 pi r square gamma. Then total delta G is equal to combination of these two, delta mu V plus delta mu S is equal to 4 pi r cube delta GV plus 4 pi r square gamma. So we have not put the signs here. We have not put the signs here. Which quantity will have positive sign or negative sign, or both will have negative sign or positive sign? What is your opinion? Delta V will have positive or negative. Similarly, delta S will have a positive or negative. This is surface energy, and this is Gibbs free energy. Yes, delta GV, delta mu V will have negative sign because there is a delta G associated. You see here, this is how it happens. Surface energy is a positive terminology, and volume free energy is negative. So this will go on decreasing. Surface energy term will go on increasing independently. But these are two events should occur simultaneously. So nucleation should form, a solid growth should take place. Nucleation is formed at the expense of thermodynamics. Solid is formed at the expense of surface creation. Both should be balanced. So if you singly monitor only volume free energy change, it will be like this. If you monitor only surface energy, it will be like this. But it is occurring simultaneously. Then the curve should look like this only. Up to certain free energy change will increase. Then once the nuclei is formed, delta G will become negative. It will decrease. Until the nuclei is formed, the system's free energy will increase, which is unstable. High energy state is unstable, and it should get stabilized by losing the energy. This half field loses the energy, becomes negative. Then the precipitation takes place. When the precipitation takes place, a solid growth is taking place, a new surface is created. The free energy change at which the solid nuclei formed is the minimum required free energy change, delta G star or delta G naught, delta G star usually. And the size associated with this nuclei is known as critical nuclei size, R star. Unless the nuclei size reaches R star, there won't be any precipitate. Unless the free energy change reaches delta G star, R star will not be formed. It's a synergetic. Delta G star and R star under synergetic. So it is like this. So once the R star is reached, then delta G will become negative, or vice versa. Once the delta G becomes delta G star, R star will be formed. In rest of the condition, the reactant or the precursors will remain in solution. Or if the nuclei size doesn't reach R star, the reactant will remain in a solution only. Gold ion will remain as a gold ion only. It will not precipitate as a gold metal atom. But once the critical nuclei size is reached, so several such nuclei will combine together and make a precipitate. This is the basis. I think this much is enough. Okay, so a critical nuclear size. What is this practically critical nuclear size mean? This critical nuclear size means this is the lowest size of nanoparticle you can get in any process. How much? What is the size? It depends on the system. We don't know. Depending on the reaction condition, reactant concentration, temperature, time, duration, nucleation pattern, etc. It depends on all those parameters. So this is the lowest particle size or grain size you can get, R star. And it is possible to quantify both delta G star and R star. It's possible to quantify both delta G star and R star as given here. R star, we should be able to reach these quantities, gamma divided by delta GB. And delta G star, 16 pi gamma cube divided by delta GB. What is delta GB? Volume free energy change. What is delta G? Free energy change. What is gamma? Surface energy. So why we are talking about the delta GV? Why we are talking about the surface energy? Because there is a creation of solid particle when you bring two solutions together. Thermodynamic favors, delta G is negative. There is a solid creation. And if it is a spherical particle, you link with the radius or volume. And it is a solid, we have a solid surface. So we are going to take a few minutes and you are going to try to get me these parameters from this equation. So the delta G for this precipitation process mathematically can be expressed like this: 4 by 3 pi r cube delta GV plus 4 pi r square gamma. Differentiate this equation with respect to radius of the particle and equate the differentiated equation d delta G divided by dr equal to 0. Then substitute r by r star and try to get me r star and delta G star. So here is an equation: delta G equal to 4 by 3 pi r cube delta GV plus 4 pi r square gamma. This is the equation. You are asked to differentiate this equation and equate it to 0. Differentiate the equation with respect to r and equate to 0. So then replace r with the r star and get the r star value. So how will you differentiate this equation? d delta G divided by dr is equal to 0. That is what I am asking you to do. So d delta G divided by dr is equal to 0. Then this equation will become 3 into 4 by 3 pi r square delta GB plus 2 into 4 pi r gamma. You replace r by r star equal to 0. Then you solve this equation. So we have delta G 4 by 3 pi r cube delta GV plus 4 pi r square gamma. So I am asking you to differentiate this equation dou delta G divided by dr equal to, so literally d by dr of this. So that I'm sure many of you will agree with me. Those who have, all of you will agree with me definitely. So differentiation of this equation will be 3 into 4 by 3 into r square delta GB plus 2 into 4 pi r gamma equal to 0. So this equal to 0. So then I told you a condition r you replace with the r star. So this equation will become 3. So this equation will become 3 into 4 by 3 r star square delta GB plus delta star, because r star, and it will become delta star, and 8 pi r star gamma equal to 0. So from this equation, try to get the r star. Try to get the r star. This is what you will get. R star is equal to minus 2 gamma divided by delta GB. Once you know R star, you substitute R star in this place and you will be able to get G or G star. This will be equal to 16 pi gamma cube divided by 3 delta GB. You please work out, take time, maybe after the classes, and try to differentiate. This is the condition. Differentiate this equation and equate R equal to R star equal to 0. Then try to get these two parameters. What are these two parameters? So R star is the minimum particle size that you can get in a process. I hope my screen is visible. Yes. And delta G is the minimum barrier energy or Gibbs energy required to overcome the thermodynamics to become negative. Very important. And as I told, I reiterate, R star is the smallest particle size that you can get. When you can get, how much it will be? Depending on the gamma and the delta GB. Depending on the gamma and the delta GB. How will you practically do this? How will you practically do this? You have to increase delta GB and you will have to reduce gamma. What is the increase in delta GB and what is the reduction in the gamma? This is what practically you will do. In order to increase the supersaturation, you will manipulate these parameters practically. You will manipulate practically these parameters. It may be a temperature, you will add some additives, you will play with the duration or time, etc. in such a way that you manipulate delta GB or you manipulate gamma. It's like this here. One practical parameter is temperature. This is one temperature, this is another temperature, this is another temperature. And this is delta G. This is similar to what we have seen here. Curve here. This curve. Where is it? This is same curve. Delta G versus particle size or radius, etc. And the reaction is conducted at a different temperature. High temperature, little lower temperature, and very lower temperature. And depending on the temperature, we have a different free energy change. And when the difference in free energy also same, the R star is also different. You will literally manipulate the reaction conditions in order to get the smaller particles. That is the take home point. Not only temperature, you will also manipulate the concentration and the time. You will also manipulate the time and temperature, concentration, and you will also add some external external additives in order to arrest the reactions. In order to arrest the reaction. By controlling these practical parameters, you will be able to, you are internally or inherently you are controlling delta G, and you are also controlling the gamma in such a way that you end up with solid particles of desired size, shape, etc. Desired size, shape, and distribution. I think we will stop now. So we will take up this in the next class. So these two fundamentals, please pardon with me, only this class will be like this. It usually happens to me. So from next class, I think it will be okay. You can go through this video and maybe the PPT I will share. So if you have anything you have to ask, you can reserve and ask me next class. Now, if anybody would like to have anything,
Sir, you will
I will share the PowerPoints after completing each unit, and videos are shared soon after the classes.
sir in Google.
Have you not seen so far any of videos, previous videos, PPTs?
No, sir.
You check with your classmates or batchmates. I have shared 3-4 days before itself. The whole Google folder I have shared. You send your email ID, I can add to that if not.
Okay, sir.
Yeah. So you would have seen that the first internal, any questions came out of the portion or out of which I have not thought? All within the content that I disseminated. Anybody would like to respond? First internal you have completed, right?
Sir, all of the questions that came from whatever you teach us, there is no problem with
Yes,
the
right.
questions, sir.
That is more than sufficient. Yes, you are correct. No need to refer anything, but you are free to refer anything. You are free to refer anything, but most of the questions will come from my content. You are free to refer anything. Okay, so I think we will stop now. We'll continue in the next class. See you.
Thank you, sir.
Thank you,
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
See you.